Hello and welcome to lecture number 32 of the course Theory of Computation, right? So we have seen Turing machines and we have seen various variants of Turing machines, which are multi-tape Turing machine, non-deterministic Turing machines. We saw the enumerator, right? So one thing that I said at the towards the end of the previous lecture was that all of these models, right, they have differences, but they share one property. The property is that they all have unrestricted access to unlimited memory, right? So this is something that DFAs, for instance, did not have. This is something that PDAs did not have, right? PDAs had unlimited memory in terms of the stack, but there was only restricted access to it, right? But Turing machines, whatever be the precise model that is used, right, whether it is multi-tape or non-deterministic, right, as long as we have unrestricted access to the unlimited memory, then they are all equivalent in power, equivalent in terms of what are the languages that can be recognized by this Turing machine, right? So in that sense they are equivalent. So the amount of time taken or amount of space required may vary from the specifics of the model used. So when perhaps non-deterministic Turing machines can do things a bit faster, right? But we are not talking about the resources like time and space. We are just talking about what are the class of languages that we can recognize with a certain Turing machine model. So the good thing is that the model is robust. As long as we have unrestricted access to the unlimited memory, it doesn't matter what exact details we have for the model. All the models recognize the same class of languages, decide the same class of languages. So we don't have to specify things like this language is recognized by a single tape Turing machine but cannot be recognized by multi-tape. No, we don't have to get into such things, because a language that is recognized by single tape Turing machine is also recognized by multi-tape. It's also recognized by non-deterministic Turing machine, right? In a way, this is similar to programming languages, right? So whatever you can program with a C language is some. So if you want to do a certain task, computation task with C language, you can do it in other languages also, like Java or Lisp or other languages too, right? So now the goal of this lecture is to kind of motivate you to what is an algorithm, right? So far we have only been saying things at a higher level. So what we want to what we want to refer to as an algorithm is exactly those set of things that are decidable, right? And as I already mentioned, like the details of the computational model, the details of Turing machine, single tape, multi-tape, deterministic, non-deterministic, all that may vary, but it doesn't matter because all of them capture the same class of languages. So something is decidable means it's decidable across these different models of Turing machines, right? So by an algorithm, I mean something like something that is decidable on a Turing machine model, right? So this is the first step towards formalizing the concept of algorithm. What is an algorithm? We are now formalizing it, right? So it is so we know algorithm intuitively, like you have a step by step intuition or step by step set of instructions, or if you're cooking something, it's like a recipe, right? So you start with this, then you do this, and then you check how much it has cooked, and then you add the other ingredient and so on. So similarly, it's also a step-by-step set of instructions, but more formally we want to call algorithms as the Turing machine algorithms, meaning what like a certain language is decidable. So how that language is decided by a Turing machine. So algorithms are exactly the class of decidable languages and how the Turing machine decides this, right? So now before proceeding, a small detour as to how a small detour about some history, right? So now we might be taking this for granted as to what an algorithm is, right? So we know what this is, we have this definition, but there was a time when this was not formally captured by any clear definition or anything like that, right? So this, as I said in the introductory lecture of this course, this formalization happened around the Second World War, around the 30s, mid to late 30s, by Alan Turing, right? But then computation was something that people used to do even from the ancient ages, right? So people had to build stuff, right? People had to transact, even in the BC periods, people had to build stuff, transact. So people used to do computations, right? But the formalization of what is a computation was only done in the 1930s by Alan Turing, right? So one of the historical things that happened was in 1900, right? So there is this 4-year conference that happens. It still happens, called International Congress of Mathematicians or International Congress of Mathematics, right? This happens once in every 4 years. So in 2022 there was one, and so this is a very prestigious meeting where mathematicians meet and discuss various problems which are of fundamental nature and which is relevant to the society as well as mathematics, right? So in 1900, David Hilbert, who is a very famous mathematician, he went to this meeting and he listed 23 problems, right? So now these problems are called Hilbert's problems because he asks questions about these problems, right? And many of these problems are now very important, very significant. So one of his problems is what you're going to talk about. It is the 10th problem that he listed. It's known as 10th problem, Hilbert's 10th problem. So if you can Google it, and there's a Wikipedia page just for this problem as well. So the problem is very simple, right? So you can even ask it to a school going child, right? So given a polynomial, you are asking whether the polynomial has any integer roots. So for instance, here I have a polynomial 7x power x minus 8x power 4 minus plus 13x cube minus x plus 10. The question is there an integer x for which this entire thing becomes 0? Right? So this particular polynomial I have not verified it. Perhaps there is, so you can try some simple things. If you set x equal to 0, then it evaluates to 10, so it doesn't work. X equal to 1, I don't know, x equal to 1, 7 minus 8 is minus 1 plus 13 is 12 minus like 11 plus 10. So so 0 is not a root, 1 is not a root. I'm not sure if there is an integer root, but you can try playing around. Right, so this is the question: given a polynomial, does it have an integer root? So just to give so there is one other polynomial that I have written here, right, in the red box: 6x cube yz square plus 3y square minus x cube minus 10. Right. So here one possible set of integer solution for this I have checked is x equal to 5, y equal to 3, and so I think there was an error in the question. So 3xy squared, right? Not 3y squared. X equal to 5, y equal to 3, and z equal to 0. This gives this evaluates a polynomial to 0 because the first term 6x cube yz square becomes 0 because z is 0. 3xy squared, this becomes 3 times 5 times 9, which is 15 times 9 is 135, minus x cubed, which is 125. So 135 minus 125 is 10, minus 10, which is 0. So this is an integer solution to this polynomial, right? So this polynomial is over 3 variables, whereas the earlier polynomial px was over 1 variable, right? But the question can be asked for single variable polynomials, multiple variable polynomials, and so on, right? So one possible approach, let's say for single variable polynomials, is to so we checked already. If you coming back to this px, we checked already 0 and 1. So you check 0, it's not. We saw it's not a root. We saw 1 is not a root. Minus 1 can be checked. So 7x power 6 is 7, minus 8x power 4 is minus 8, so minus 1, plus 13x cube. So that will be again minus 13, so you get minus 14, plus minus x, so which is plus 1, so it is minus 13, plus 10 is minus 3. So even this is not a root. So we have verified that 0, 1 and minus 1 are not root. And then you check 2, then you check minus 2, then you check 3, minus 3, and so on. So you keep checking, right? So you check whether 0 is a root, 1 is a root, minus 1 is a root, 2 is a root, minus 2 is a root. So like that, basically what we are doing is you take the real line, you check 0, you check 1, check minus 1, then you check 2, then you check minus 2, and so on. So basically you are covering all the integers in the line by going back and forth, 3 minus 3, 4 minus 4, and so on. So all the things are covered. So now you may be able to figure out that this is an algorithm, or this is an approach. I don't want to say algorithm, but suppose there is some integer solution. Suppose, for instance, 50 is a root, right? So then when we do 1 minus 1, 2 minus 2, 3 minus 3 up to when you reach 50, it says it's a root, and then we can say yes, 50 is a root. There is an integer solution, right? But if there are no integer solutions at all, this process never ends. You check 1 is a root, 2 is a root, minus 2 is a root, all that you go back and forth, and you never end. You're just cycling through all these infinite integers, and you will never stop. You will stop only if there is a root, right? So therefore this is a recognizer, right? So, and not a decider, right? So if the answer is yes, if there is an integer root, it will stop and say this is the integer root. If there is no integer root, it will not accept, it will not say yes, right? If the answer is no, it will not say yes, but it will not say no also. There is no way for it to stop, because it just continues computation. In that sense, it is not a decider. A decider has to always halt. If it has an integer solution, we want to say yes. If it does not have an integer solution, we want it to say no and stop the computation. But this does not stop. Right, so it continues computation, and it never says yes, but it never says no also, right? Now, can we convert this to a decider, right? Maybe I'll just erase this, but this approach can be converted to a decider? That's the question. Can we convert this to a decider? Now, if there was some bound, let's come to single variable, right? If there was some bound, let's say you only have to check, like if there is a root, it is going to be less than 100. Let's say somebody tells you, then that is a decider, because we check 0, 1, minus 1, 2, minus 2, and so on, and up to 100, minus 100. Let's say then if it is a root, if there is a root, it's going to be of size or absolute value less than 100. So up to 100 minus 100 we do, and then if we do not find a root, we say that this does not have an integer root. So if we have a bound, then that bound can tell us this is the place where you can stop. You don't have to check the infinite possibilities, right? So if there is a bound, that is a way to convert it into a decider, right? So this works for a single variable polynomial, which is what Px is about, right? For a single variable polynomial, we can get a bound, right? And this bound can help us make it to a decider, right? So in fact, this is a problem in the textbook 3.21. So basically it asks you to find a bound for a given polynomial. So given a polynomial which is of single variable or a univariate polynomial, it asks to find a bound. So it asks to say that if x is a root, then x is at most something, right? Or the absolute value of x is at most something. However, this bound only works for the single variable case, and for multivariable case there is no such bound, right? So because there are multiple variables involved, how do you bound it, right? Or maybe single bound works for all? No, but we don't have such a bound. In fact, it was shown by Matiasevich in 1970, right? So building on the works of others by Davis, Putnam, Robinson, and so on, there people worked on this problem before. So but the final piece of the puzzle was provided by Matiasevich, and sometimes it's attributed to all four of them, Matiasevich, Robinson, Davis, and Putnam, that there is no decider for this problem. In the general case, general is multivariable case, there is no decider, meaning we cannot write an algorithm for this question. So this is a recognizer. A recognizer is not an algorithm. You always want to halt, right? A recognizer does not halt or may not halt. But what we know is that there is no algorithm that exists for the 10th problem. Or in other words, the Hilbert's 10th problem is undecidable in general, right? Meaning there is no algorithm for it. So this this approach that I highlighted above, right, this is a recognizer, not a decider. What Matyasevich showed, building on the work of others, is that Hilbert's 10th problem is undecidable. Right. So this was a big deal. Like, something was asked in 1900, and finally in 1970 it was shown. And for this, one has to say what, like, so Hilbert's question was posed, like, is there a procedure by which we can find this? But the theory of computability had to be built in order to answer this, right? And this theory was built by Alan Turing in the 1930s. There was also a parallel body of work by another mathematician called Alonzo Church, right? So together, not together, but independently, they built two separate notions which actually kind of coincide, right? So therefore, this is so without getting into all the details, the point is this: what they say is that the intuitive notion of algorithms. So we have an intuitive notion, like a step-by-step approach, and we want a solution. We don't want it to halt, etc. This is identical to the Turing machine deciders, right? So Turing machine deciders. So the intuitive notion of algorithms is the same as Turing machine decider. So if you want to formally show something has an algorithm or does not have an algorithm, you have to show it is undecidable, right? So this is what we mean. This is what we mean by Church-Turing thesis. So it was posed by it was said by two mathematicians, Alonzo Church and Alan Turing, right? So it says that intuitive notion of algorithms is the same as Turing machine algorithms, right? So this history was to kind of motivate this Church-Turing thesis. So such a fundamental problem, to answer this, the theory of computability and the Church-Turing thesis had to be formulated, right? So what we said is that is what is an algorithm, and we talked about the Hilbert's 10th problem in order to motivate that. The next thing is about now some details about how, now that we have come to an understanding of what exactly constitutes an algorithm. So it is what a Turing machine can decide, right? So one question is, how do we decide or how do we give something as an input, right? So sometimes the problems are itself not clear as to how, like, are not, like, let's say you have a graph. Now how do we give the graph as an input? Or suppose sometimes you can ask questions about, let's say this, like, I have a Turing machine and let's say I have a PDA. I want to ask whether this Turing machine and this PDA recognize the same language, right? So how do we specify the Turing machine as an input and the PDA as an input, right? So these kind of things, how to specify inputs and how, some more details I want to just talk about that, right? So one point is that so far we have been talking like we could, when we talk about Turing machines, we could go into various depths of detail, right? So the most detailed is that I can talk about the transition functions, delta, qi, states, individual transitions when it go one step right and write a symbol b and so on, or one step left and so on, right? So this is at the level of state and transition function. We will not be doing this level. The one step higher level is about head movements. So you scan the input, go to the rightmost end, and then you put a symbol there, then you come back to that kind of, where you specify what the heads do and how you plan to change the tape content, etc., right? Or how you plan to verify the tape contents. Even this level we are not going to be talking about from now on. From now on, our discussion is going to be at a high level where we describe the algorithm in just English, right? So we will say that you take the input and then you check something, right? So for instance, given a graph or given a, how do we specify a graph as an input, right? So you may have seen in data structures, and even in one of our previous lectures, we talked about this this way to specify a graph called the adjacency matrix. So given an input string, we want to verify it's a proper adjacency matrix. So it's simple. We can just check whether it is a square, right? So the number of entries is a perfect square. So the matrix will be entered as, let's say, all the entries of the matrix. So if it is an n by n matrix, all the n squared entries will be provided in a serially, right? So the number of entries is a perfect square, and you also have to check there is symmetry of the matrix. So the adjacency matrix of an undetected graph is going to be symmetric. This also I think I mentioned in, I think, 2 lectures back. So you also have to check that whether the ijth entry is equal to the jith entry. So this is how you would verify whether a given input string corresponds to an adjacency matrix of a graph, right? So this is how we will deal with things. So what we are going to do is to not talk in the level of the machine or at the level of like head movements, etc. We are only going to be talking about high level, unless we have to go into the machine level detail, right? So for instance, another thing that you can ask is, given an input string which corresponds to a graph, does this correspond to a connected graph? Is this graph connected, right? So we know algorithms from the like graph algorithm scores. We can do traversals like breadth first search or depth first search, right? So of course, before that we can only do it if the thing that is given to us is actually corresponding to a graph. So we first check whether the input corresponds to a graph. If it is not of the proper form, right? If it is not a 0-1 adjacency matrix, then we immediately reject it. Let's say if it is a 0-1 string but it is does not correspond to an adjacency matrix, then also we reject it. If it corresponds to a graph, now we know what graph it is, and then we can execute the breadth first search or depth first search, and we accept if it is connected, reject if it is not connected, right? Another problem, like given a string, is it a prime number? Given an integer, is it a prime number, right? So these are all questions that we can ask. And like I said before, we can also ask questions about, given a DFA, does it satisfy some property? Given a Turing machine, does it satisfy some property? So we will have to encode the given, like we will have to provide the DFA as an input or provide the Turing machine as an input. So how do we encode? You could encode in many ways, but one way is you can have this encoding with zeros for the input symbols, right? So this corresponds to the encoding of the input symbol. So blank is given the encoding 0. First symbol, let's say A1 is given the encoding 2 zeros, A2 is given 3 zeros, A3 is given 4 zeros, and so on. So how many ever input symbols are there, we could have that. And similarly, accept state is given 1 0, reject state is given 2 zeros, start state is given 3 zeros, then Q1 is given 4 zeros, Q2 is given 5, and so on, right? And so zeros is used to encode symbols as well as states, right? Now if you want to encode a transition function, right, let's say like this, delta Qi Aj is Qp As and R, meaning when you read Aj from the tape, and when you are in state Qi, then you write As onto the tape, the symbol As, you go to state Qp and then move one step right. So this one we can encode it like this. So Qi is denoted by 0 power I plus 3 zeros, because if you see Q1 has 4 zeros, so Q2 will have 5 zeros and Qi will have I plus 3 zeros. Aj is denoted by 0 power j plus 1. So A1 has 2 zeros, A2 has 3 zeros, so Aj will have j plus 1 zeros. And then Qp will have p plus 3 zeros, As will have s plus 1 zeros, right? And I am using ones as delimiters, right? So I'm explaining how to encode this transition function. So these ones are delimiters. And finally we have the right movement. Right is denoted by 2 zeros. So I could also have denote left by 0, right by 2 0, etc. So this entire string denotes this rule that is highlighted, the transition function of the Turing machine. So like that, this is just one snippet, one part of the Turing machine. So the entire Turing machine set of rules can be encoded in this manner, right? So the point here is to convey that this can be done, not really get into all the details, but this can be done and we can do it. So now, from now on, we'll just assume it can be done, right? So, and similarly we can do, so even for a deterministic finite automata or push down automaton, we can encode in the similar way, right? And we can ask questions. So I can ask, like, given a Turing machine M, right? So I can give it as input. I can ask, does this Turing machine accept only palindromes? Right? Is there a so that it's a yes no question, right? Does the Turing machine only accept palindromes? Or I can ask, is there any palindrome that is accepted by this Turing machine, right? Or I can give a Turing machine M and a string W. Is this string W accepted by this Turing machine, right? I can ask these questions. I could ask questions of DFAs, NFAs, etc. So some languages which have some names. So we'll see more of them in the upcoming lectures, upcoming weeks. So ADFA, right? ADFA is a language where you're given a DFA and a string, and you're asking whether this DFA accepts the string. So it is a set of all pairs BW, where B is a DFA that accepts W, right? So this is called ADFA. In fact, the language that I described earlier here, right, this language, given a Turing machine M, does M accept W? This is denoted as ATM. It's like the acceptance problem of a Turing machine. So this is ADFA is acceptance problem of a DFA. Similarly, we can ask ANFA. Does a given NFA accept a given string, right? I could ask EDFA. It's like the emptiness problem, right? EDFA, given a DFA, is the language accepted by this DFA the empty language, right? I could ask EQDFA, the equivalence problem. Given two DFAs, are they equivalent? Are the language recognized by them the same, right? EQDFA. I could ask acceptance problem for a context-free grammar. Given a grammar G and a string W, is a string W generated by this grammar, right? So I can ask all these kind of questions, right? So the point that I want to say is that almost for any question we can encode and pose it to a Turing machine, and a Turing machine can do some processing or some algorithm, and if such an algorithm is possible, it may be able to provide such an answer. So in computability theory, we are going to be asking questions of this type. Can we, we started by asking this Hilbert's 10th problem, right? So given a polynomial, can we tell whether it has an integer root or integer solution? And then we learned that this is an undecidable problem, meaning there is no way you can write an algorithm for it. There is no way you can build a decider for it. So now we are going to, in the upcoming lectures, we'll ask questions like this, like is a DFA a decidable problem? Given it DFA and a string, can we tell whether this string is accepted by this DFA? Is a TM, given a Turing machine and a string, does this Turing machine accept the string? Is this a decidable problem? So we are now going to get into decidability, undecidability theory. So we are trying to, so this was a precursor to that, right? So in order to understand that, we first formalized the notion of algorithms, which we said is going to be deciders, and we stated the Church-Turing thesis. Now we are explaining how almost anything can be specified as an input to a Turing machine. And in the next upcoming lectures, we are going to focus on these languages like these, and see whether we'll try to understand whether they are decidable, whether they are recognizable, etc. So we'll see that there are languages that are not decidable, there are languages that are not even recognizable, right? So surprising as it may seem, there are such languages too, right? But with this we conclude week 6. This also concludes chapter 3 in the textbook, right? So in week 6 we saw variants of Turing machines. We saw the Church-Turing thesis, which is in this lecture, and we set the stage for the decidability theory that is going to come in the remaining weeks. So that's all I have for you in lecture number 32 and in week 6. So see you in week 7. Thanks.